Okay, this lecture is over DHCP, which stands for Dynamic Host Configuration Protocol. The purpose of it is primarily to assign networking information to the device. One other thing it does do is provide what I'm calling other information, like DNS servers, network time servers, that type of information. Now, before DHCP exists, there were a couple of things that are considered predecessors to DHCP. The first was reverse ARP. So we recall that ARP, we have an IP address, we make a query, we get back a MAC address of the device we need to communicate with, either the device that has the IP we requested or the default router that we need to send to so that the packet can make it to its destination. Another protocol is BootP. In the 70s and 80s primarily, we had these things called diskless clients. So these were like a computer that did not have a hard drive, basically. So in the case of BootP, when a machine started up, it would make a BootP request, and a BootP server would come back and say, here's your networking equipment, and here's the location of an image that you can download and boot from. So the process for DHCP is very similar to what I just described in BootP. The client broadcasts a DHCP query, and any DHCP server that quotes knows, we'll come back to that in a moment, knows the client or is configured to answer queries can send a response giving the information to the client that requested it. Now, in some cases, your BootP tab, which is what DHCP uses, has IP addresses and MAC addresses for all the clients on your network. In a bigger environment or easier to set up, you can just tell the server, answer any DHCP request you get, assign it an IP out of these ranges. So you can do that with the DHCP server. Most modern day routers run a DHCP server on them so that when you start up devices in your house, whether they be smart TVs, smartphones, laptops, desktops, etc., so that they get an IP address. Again, that's typically configured to come out of a pool of IP addresses. DHCP has something called a four-way handshake, and it looks like this. So a DHCP will send a discover, and hopefully a DHCP server responds and says, I'm going to offer you this IP address. And then the DHCP server, if it's happy with that, turns around and says, hey, I'd like to have this IP address that you just offered to me. And the DHCP server would come back and acknowledge that. First time I looked at this, I thought the offer and then request for the same IP was kind of weird. I actually did a search to find out when a DHCP client might decline the offer. And the one situation that seemed to always come up was if it was given an IP address that it can determine is already used on the local network. It doesn't want to create an IP conflict, so it would come back and decline that offer. This is what a DHCP discover packet looks like. We'll talk about these individually, but we have the things shown in the graph. And after the last box shown, the gateway IP address, the fields were pretty large and or variable. So instead of drawing them in picture form, I just listed them in the order they appear. so that I could get it all on one slide and not spend a lot of time trying to group cells and everything in my table. So the first thing we have is an opcode. It's 1 byte in length, and it specifies the type of DHCP message that is contained in the packet. For example, a 1 is a request and 2 is a reply. Hardware type, when all this was set up, we had a hardware type, and we've seen this before. I can't remember where, maybe ARP packets, but it specifies the type of hardware that is being used on the local network, and very common is for this value to be set to 1, which means Ethernet. We have something called H-length, which is 1 byte. It's the length of the hardware address. For a MAC address, this would be 6 because there are 6 bytes to make up the 48 bits that are in a MAC address. We also have something called hops. This is set to 0 on clients, but if we have a relay agent in our network, this is used to control forwarding of the DHCP request. We then have a transaction ID. This is a number that is generated by the client, and the purpose of this is when we get a DHCP response so that we can match it up with the request that was being made. We have something called seconds. This is the number of seconds since a client initiated a request or a renew request. Next we have flags. Flags are 2 bytes or 16 bits. For boot P, these are empty, and if we are using this, we only use the very first bit. The remaining 15 are considered reserved, and it is set to 1 if the client does not know its IP address. Therefore, the server can't respond directly back to that client, so that's telling the server that the reply to the DHCP request should be broadcast so that the client hopefully sees it. We have a client IP address. This is the sender's IP address. We have something called your IP address. This is the server coming back and saying, this is what I'm assigning as your IP address. So that's what the client should set its IP address to. The server IP address, if the server chooses, it can put its IP address in these 4 bytes. We have the client hardware address, we have the gateway IP address, which is 4 bytes. This is used when we're using relay agents. We then have the client hardware address, which is 16 bytes. This is the layer 2 address of the DHCP client. Not really sure what hardware addresses are 16 bytes in length or if they were trying to plan for the future, but obviously for MAC addresses we would use only 6 of those 16 bytes. We can put the server name here, which would be like dhcp3.domain.com, for example. That can be up to 64 bytes in length. We have a boot file, which can be up to 128 bytes. In a request, you can ask for a specific boot file. When the server is doing a response, it's going to say, here's the boot file you should boot from. And then the last thing we have is options, which is listed as being variable size. This was originally called vend because it was a vendor specific area, and we will discuss the different types of things and how to use that field starting on the next slide. The options field starts with a 4 byte, what's called a magic cookie. This is a very old term. In Kerberos and things like that, you had something referred to as an MIT magic cookie. But in BootP, this was vendor specific. So it was a hex value or a 4-byte value specified in hex that represented who the vendor was, and therefore you would know what was in the options field based on the vendor. For DHCP, it is this hex value shown here, 63825363. Then it is followed by sets of 3 things. You have a 1-byte option code, tells what the option is. You have a 1-byte option length, and then you have the option data, and it is of the length specified in the option link, the second field. So let's look at a real life example. So here is a DHCP packet that I grabbed. I clicked on, it says BootP, even though it's DHCP. So since I clicked on that and it's highlighted in blue, the entire DHCP packet is highlighted on the right side in blue. So we start out with the opcode, which is 1. That means this is a DHCP request. The hardware type is 1, which I said earlier stands for Ethernet. The hardware address length is 6 because we have a MAC address. We have hops, which is 0 because this is a discover, which means the client is sending this message. Here is the transaction ID. And then the seconds is set to 0 because we're not using a relay agent. And then our flags are all 0. Again, that makes the first bit 0, which means the client does know its IP address. The client IP address is all 0s. Your IP address is all 0s because this is a request. This would only be set in a response. The server IP is all 0s because it's a request. The gateway address is all 0s because there are no relay agents. Here is the hardware address. So the first 6 bytes are the MAC address, and the rest is padding because we don't need the other 10 bytes for our MAC address. This is where the server name would be. These are all 0s, so no server name was given. This is the boot file. None was requested, so it's all set to 0s. Here's the magic cookie that we talked about. That means the value specified means DHCP. And then I kind of move this down so it's a little easier to see. So now we're looking at the options after the magic cookie. So option 1 is 35 in hex. 35 in hex is 53 in decimal. And 53 means this is a DHCP discover. Its length is 1 byte. And the data is a 1, which means, again, it is a discover. The second option starts with 3D, hexadecimal. 3D hex is 61, which means I'm going to give you a client ID. The length is 7 bytes. And the data first has a 1, which means Ethernet. And then it has the MAC address. The third option has an opcode of 35 hexadecimal, which is 50. This means requested IP. the length is 4, and all zeros on a requested IP means I have no preference, give me whatever. The fourth option has an opcode of 37 hex, which is 55, which means I'm going to give you a parameter request list of parameters I'm requesting. The length of that request is 4, and then these are the 4 requests. So the first one, the 1, means I want a subnet mask. 3 means I want a default router. 6 means I want DNS servers. And a 42, which is 2A hex, means I want the network time protocol server address as well. And then the fifth option, which is not really an option, is FF. All bits set to 1, which is 255, and this means this is the end of the option list. And then we have some padding here, which is just some zeros to finish off space that we did not need. So that's some discussion on the DHCP protocol in in-depth packet examination of a DHCP request.